Good afternoon, everyone. Welcome back to the second talk this semester for our seminar on the mean curvature flow. We're going to have Vishnu continue to talk to us. Last time he talked about gradient estimates, and he will continue to do gradient estimates today, possibly filling in some of the proofs that we didn't quite get to last time. Thank you, Vishnu.
Thanks, Tim. So I'm just going to continue on with proving this estimate that I started with last week. But maybe let's just have a quick reminder. So last time, I wanted to prove this theorem here. Right. So if you have a smooth mean curvature flow, well, where such that the initial surface has this property that it's in this class of, well, in this pinching condition C alpha, then there exists two constants, C1, which depends on n and alpha, and C2 just depending on n. Actually, other way around. C2.
Actually, Vishnu, sorry to interrupt. Maybe you could just remind everyone what R and alpha were measuring.
Yeah, so R and alpha, well, R plays the role. Basically, they're just constants that depend only on the initial condition. So if you have just any hypersurface that's in CR alpha, for where alpha is this triplet, where if so it's like uniformly two convex, lambda1 plus lambda2 is greater than or equal to alpha 0 h, h is greater than or equal to alpha 1 r inverse, and mu and the area of m is less than or equal to alpha 2 rn. So we use this condition because under mean curvature flow, this is preserved. And the reason that we have this distinguished r is because if I scale x by lambda, then the new lambda x is in the class C lambda r alpha.
So is it right to say that alpha 0, alpha 1, and alpha 2, they're just keeping track of the quantities you've got there?
Yeah,
that we're quite
there's some
interested
quantities,
in,
yeah.
Whereas
and
R is just taking care of the scale.
That's it.
Okay, cool. Thank you.
Yep. Yeah, and yeah, okay. All right. Yeah, so if you have these, there exist these two constants such that the gradient of A squared is less than or equal to C1 A to the 4 plus C2 R to the minus 4 for T greater than or equal to R squared on 4. Okay, so, well, the strategy of the proof, continued, was to try and estimate this quantity. Just by a constant that depends only on n, because if we have that, well, okay, I'll say what GK, and I'll remind everyone what GK and GK are in a moment. But then if this is true, then we have nabla A squared is less than or equal to Cn GK G2K, which is then less than or equal to Cn. Constant might change. GK squared plus G2K squared. And this GK and G2K, they can be, so they involve either terms that look like A to the power of 4, H squared, A squared, or H to the 4, things like that, and a constant, right? And all of these can be controlled by A to the 4, right? So all of these are less than or equal to some constant depending on n, A to the 4. So this allows you to get A to the 4. This allows you to get an inequality of this form. So what we did last week was we computed some evolution equation. Okay, I should say what G is, shouldn't I? So G epsilon is equal to 1 on n minus 1 plus epsilon H squared minus A squared plus 2 C epsilon R to minus 2. So this constant C epsilon, for any epsilon, I know that from the cylindrical estimate, there exists some constant C epsilon greater than 0, such that this whole thing, such that this whole thing is greater than or equal to C epsilon r to the minus 2. So in the cylindrical estimate, what you actually have is this thing is greater than 0 with a 1 here instead of a 2. So if I put a 2 there, then I know I have this fact. Okay. So now this constant K was some, well, if you, I think I mentioned this last week, if you wanted to prove this from scratch without knowing what to choose for K, you would just put an epsilon here, put a delta here, and then you do the whole calculation and try to figure out what K you need, what you need to choose for epsilon and delta to make all these calculations work. But I read the paper, so I already know what this is supposed to be. And yeah, what was it again? It is, yeah, it's half 3 on n plus 2 minus 1 on n minus 1. So it's some constant that helps with everything. And it's very, yeah. So it's very closely related to the fact that we have this inequality. So last week I used this. It was very important that I had this inequality a lot when I was doing some calculations last week. So yeah, so last week what I calculated was, we saw that, well, maybe I should just check what I got up to. So yeah, so we calculated just what half of the problem. We saw that partial t minus Laplacian of the derivative of a squared divided by gk is less than or equal to cn plus 2 a squared derivative of a squared gk minus 2kn plus 2 on 3 derivative of a to the power of 4 gk squared plus higher derivative terms, which are not very good. But we'll see that those are all actually, we can actually see that those are actually negative. Minus the norm of the Hessian of A squared. Okay. So this is what I got up to last week. So conveniently, it turns out that this quantity here, we can just throw it out. It has the correct sign, so we can throw it out. But let me do that calculation, so that because maybe it's not so simple, not immediately obvious, at least. Okay, so let's just calculate. Let's just expand this term to see, because if you expand this term, you expect to have something that has a Hessian of A. So to see if it does anything good, let's expand that. So you get this. Okay, so that's equal to derivative of gk, and then so differentiating the top part, you get this divided by gk minus derivative of a squared times derivative of gk divided by gk squared. Okay. And that, you get a norm of gk here, and then you get, so what you get is, you get 1 on gk yeah, 1 on gk times this inner product. And then you get minus, so what do you get? So you get this divided by gk squared. Well, I'll put that at the front. Okay. I'm just checking with my notes. I think I have a lot of sign errors in my notes, but I'll just see if I can get it all right here. Okay, so that's equal to, so here we get 1 on GK times, all right, so let's just write these out in coordinates. So let's see. Okay, so here I have a nabla I GK inner product with, so I have this I, and then I have a nabla J A K L, nabla J A K L. Okay, so just with this term, I can use Cauchy-Schwarz to give me this. So I get 1 on GK times this, nabla GK times nabla A times the Hessian of A, minus 1 on GK squared, nabla A squared, nabla GK squared. Okay. Oops. Yep. And so from that, I get that's less than or equal to, let's see. So what do I need to do here? So I get less than or equal to 1 on GK squared. Sorry, I'm just trying to look at my notes, and it doesn't seem to, just made a mistake in my notes. I'm trying to figure out what it should be. Okay, I see. Okay, that's what I need to do. Okay, so then now what I've done in my notes, I've used Young's inequality here. So I get 1 on GK, nabla GK times nabla A, nabla squared A, minus, and then I have 1 on GK squared, nabla A squared times GK. Oh, sorry. No, I'm doing the Young's inequality on the wrong thing. Okay, so that's less than or equal to minus 1 on GK squared, nabla A squared, nabla GK squared, plus 1 on GK. Then I want to split up these two. So I get 1 on GK, nabla GK squared, nabla A squared, plus GK, nabla squared A. Okay, there we go. That is looking better. So the point is that now we have this Hessian term with no GKs in front of it, which means that we can cancel out this term here, right? So, yep, and so that gives us so yeah, 0. Okay, because this cancels out with that. And then, oh, sorry, no, it doesn't give us 0. It just gives me this. Okay, so then when I add these together, then I get 0 there, less than or equal to 0. Okay, sorry about that. Then I get partial t minus Laplacian of nabla A squared divided by GK in the end is less than or equal to just the, you can throw out all the higher derivative terms, you just get Cn plus 2a squared nabla A squared divided by GK minus 2k n plus 2 divided by 3. Nabla 4 on GK squared. Okay, that's good. Now we just need to do this one more time. So let's do that. Partial t minus Laplacian. So nabla A squared divided by GK. And now we just want to do the G2K. So let's just remember what the formula is for when you compute the heat operator on a quotient. So first you get partial t minus Laplacian of the thing on the top divided by G2K minus this part times the heat operator applied to the denominator. Okay, so I calculated this last week. So what was that equal to? So maybe I'll just write it on the side. Partial t minus Laplacian of G2K we calculated was, I have it up here, I think. Minus 2a squared times the G2K. I think it should be less than or equal to minus 2a squared G2K. Plus, yeah, I'll put the gradient terms up here because they're not important anymore. Okay.
So then there's a gradient term, isn't there, from that quotient formula? But I guess that also doesn't matter. Is that right?
Yeah, that's exactly right. I put it up here.
Oh, I see. Right.
Is
okay.
that right?
Gotcha.
Yeah, it's not important anymore, but
yeah,
we just need these parts. Okay, so then we get less than or equal to Cn plus 2, just plugging in formulas here now. Minus 2kn plus 2 on 3. I'll just move this away. Oops. It's a bit hard to select in this thing. Okay, forget it. I'll just leave it there. Over G2K minus, so then I get a plus nabla A squared on GK to norm A G2K on G2K squared. So we can simplify this all and factor out everything to get less than or equal to nabla A squared on G2K GK Cn plus 4 A squared, yep, minus 2k n plus 2 on 3 nabla A squared on GK. Okay, so what we have is we have something that looks like this. So we have partial t minus Laplacian of f. So f is equal to, so f equals, I'll write f for this thing, nabla A squared on G2K GK. That's less than or equal to f. And then we have all this stuff on the interior, on the inside. But what I want is this to look something like, let's say C, let's say, just write a C1 n A squared plus C2 of n, f. Okay, so if f attains an interior maximum, then I know that this quantity has to be positive because f is already positive. I already know that nabla a squared is positive and these things in the denominator, they're both positive. So then I need to know that this is positive as well. Okay, so what's this thing on the inside that needs to be positive? So let's suppose that at x0, t0 in the interior, we have a maximum point of f. So then you need 0 is less than or equal to, at that point, we have Cn plus 4 a squared minus, okay, I'll just write it there, 2k n plus 2 on 3, nabla a squared on gk. So I want this to be f, so I'll divide both sides by g2k. Okay, so in the end I have something like this. What I want to do is after rearranging this, I want to show something like nabla a squared divided by, f is less than or equal to. So all the constants I have, they all depend just on n. So I just want some constant c of n a squared on g2k. So as if I can bound a squared on g2k by a constant that depends only on n, then that's enough. Okay, so let me first just write out what this is. So that's a squared on, so g2k, so g2k is equal to 3 on n plus 2 minus 1 on n minus 1 plus 1 on n minus 1 h squared minus a squared plus c2k minus 2. Okay, so so I can write that as let's see, that is greater than or equal to, I can just write it in terms of h squared equal to, okay, actually, yeah, okay. Sorry. So what I need is, so if a squared on, let's write this, well, that's just 3 on n plus 2. If a squared on g2k is less than or equal to c dash n, then that implies that a squared is less than or equal to 3 on n plus 2 h squared c dash n minus a squared plus c2k. Oh, okay, I can yeah, okay, I'll just get rid of this part because it's not important for this part. So let's a squared. So just rearranging, all I need to prove is some kind of inequality that's like, well, I've used c a lot, so I'll just continue to do that. C dash n a squared let's so if I want something like this to hold, all I need is an inequality of the form a squared divided by h squared is less than or equal to something that depends only on n. Okay. So I actually, when I was reading the paper, I got very stuck here because I thought this was not possible. Because, for example, for mean convex mean convex surfaces, you definitely can't bound every mean convex surface, this quantity a squared on h squared, for every mean convex surface by a constant that depends only on the dimension. It seemed too good to be true, but well, I asked Ben about it, and then he explained to me how this works. But I thought it was a very nice thing that only happens for, well, okay, it happens for, I guess you can do something similar for m convex surfaces, but for two convex surfaces, it turns out you can just bound this very simply in terms of n. Okay, so remember that whenever you have a bound on something like this, so a is the sum of the principal is the sum of the squares of the principal curvatures, a squared, and h squared is the square of the sum of the principal curvatures. So this is really just an algebraic inequality. So if you want to prove something like this, you should just look at the space Rn of principal curvatures. So in this space, the two convex points, if it's two convex and all the points on M satisfy this inequality, lambda1 plus lambda2 is greater than or equal to 0, right? So that just says that the surface is two convex at every point. Okay, so we're trying to find out the max on gamma 2 of a squared on h squared. Right, so that's equal to the max on gamma 2 of, well, lambda a squared on lambda h squared, right? So just moving the lambda onto this set here, then I get it's equal to the max of lambda gamma 2 a squared on h squared. But this is scalar invariant, so this is the same thing, okay? So we could just choose lambda. I'll just write that down. So it's equal to, yeah, lambda. This is equal to gamma 2. So I can just choose lambda so that lambda h is equal to 1. And so I'm really just maximizing on gamma 2 intersect the points where h is equal to 1, a squared. But a squared, when you're thinking of like just a set in Rn where the coordinates are the principal curvatures, a squared is just the length of the points in the set, right? So this, if I'm trying to bound this, I'm trying to show that this thing is finite, that's the same as saying that this set here is compact. Okay, so that's what we need to prove. So let's assume that it's not compact. Then there exists some sequence of points such that the length goes to infinity, right? But since we're in this gamma 2 space, then, okay, well, if this is the case, then that means that since lambda 1 to the k plus lambda 2 to the k is greater than or equal to 0, then I need lambda 1k to go to minus infinity, and lambda 2k is greater than or equal to lambda 1. So this has to go to plus infinity. Okay. But then h couldn't possibly be 1 if n is greater than or equal to 3, right? Because hk equals lambda 1k plus lambda 2k plus lambda 3k at least. And these might be finite, but then lambda 2 is less than lambda 3. So all of these go to infinity, which is not 1, right? So if n is greater than or equal to 3, then this set is compact. So you know
I guess that could be a good exercise for optimization theory students.
Yeah, I mean, well, actually, yeah, I mean, I think also if it's M convex, I think, and N is greater than M, then is compact maybe, I think.
The exercise is to work out the best constant.
Ah, yes.
Oh, right, yeah, that would, okay, I didn't do that. Actually, I did try to do that. I tried to algebraically figure out what this actually was, but then I don't know, it took too much effort, so I stopped. Okay, so now we've bounded this by a constant, and so we know that, so we're basically done here with this gradient estimate. So now I want to do, maybe with the remaining time, I just want to go over some of the immediate consequences. Well, okay, not that immediate. Well, I did a very long calculation, and I think, you know, it's maybe less illustrative to do another really long calculation. So I'll just state this theorem, which is the second derivative estimate. So I don't think there's anything more to learn. Oh, well, okay, there is a little bit more to learn, but I think the gradient estimate, the first derivative estimate, is harder to do than the second derivative estimate. So, so you can, in the paper, you can read how to do this properly, right? So the same thing, if x0 is in C alpha, then there exists C1 dash depending on n, and C2 depending on n and alpha, such that the Hessian of A is bounded by C1 dash A to the 6 plus C2 dash R to the minus 6 for T R squared on 4. Okay, so this is basically just another application of the maximum principle and then using the first derivative. Okay, and then if you read this proof basically, you can use the same method in the proof of the Hessian estimate to also get the higher derivative estimates. And also if you use the evolution of A, so remember that okay, well, I'll just write it down. Partial TK, partial L A, so that's equal to C1 KL. And this is some number N that depends, oh, well, I should use that, M that depends on K and L. It's not so important here what it is. Plus C2 KL to the minus M KL. So, you know, I said that this is kind of straightforward, but it's actually not that straightforward, because in the actual paper, all of these need to be proven in the presence of surgery, right? So for that reason, it's actually these higher derivatives, I think, I mean, I don't really know exactly how it works, but they're slightly harder to do. Because for example, in normal parabolic equations, once you have the first and second derivatives, you can get all the higher derivatives. But now, when you're doing surgery, it's actually in the presence of surgery, you can't go as high as you want anymore with these derivatives in the presence of surgery. Right? So in the presence of surgery, something like this only holds if you have some kind of, for some, not for I think something like 2K plus L less than some constant. Okay. And then, you know, if you're just in the smooth part of the flow, then, this holds for all L, K, and L. Also, and maybe I should say one thing about how do you get the time derivative? Well, you know that the time derivative of A, that is equal to, oh wait, yeah, equal to Laplacian A plus A squared, right? So it only depends on, if you've bound the derivatives of A, you can also bound the time derivative of A. Okay. All right, so let's see. Okay, I'll do this one more theorem and then we can stop. So using gradient estimate, you can, if you have a bound on the derivative of a function by some constant in a neighborhood of the function, then you can integrate the derivative to find out how big the original function can get nearby. Okay, so that's what the point of this is. All right, so if you have, okay, actually, okay, let me state this corollary. So we have these bounds on A, but we can easily make those bounds on A into bounds on H and its derivatives. So if your initial surface is in CR alpha, then there exists some constant H0 and C0, which depends on n alpha, both depending on n alpha, such that if Hxt is greater than or equal to H0, then the derivative of H is less than or equal to CH squared. And you can also bound the time derivative of H. So, I mean, we already have bounds on A and it's on the derivatives of A. So we just need to use these properties. Squared. Okay, and then that's it. Just apply these properties to the original theorem, to these theorems, and then that works. So now I want to show that if from these gradient estimates, you can show that near a point where the curvature is some value, then nearby the points, the curvature can't increase or decrease by too much. So, okay. So let's say, I mean, well, let me phrase it like this. Okay, so if I have a closed mean convex mean curvature flow, where I know that the gradient of H is bounded by CH squared, and the time derivative of H is bounded by C squared on 2H cubed. Then for any YS, okay, in a parabolic ball of radius CH xt, centered at some point xt. Also, this parabolic ball, maybe I should define that PR of xt, that's equal to, well, okay, intrinsic parabolic ball, that's equal to the intrinsic ball of radius r at x times t minus r squared t. We have this property. So the mean curvature at ys is within this bound of the mean curvature at x t. So to show this, we just need to first integrate this equation so basically the proof is you integrate this equation to get a bound between the mean curvature at yt and the mean curvature at yt and xt. And then you integrate in time to get him to move in the time direction. Okay, so proof. Let's take a unit speed geodesic. Gamma is a unit speed geodesic. Connecting x and y. X and y at time t. Okay. So then, well, I know that if I differentiate h inverse, so the derivative of h inverse is the derivative of h divided by h squared, right? So this here is bounded by c. Okay. And integrating this equation along the curve gamma, then I get minus c r is less than or equal to h xt inverse minus h y t inverse, which is less than or equal to cr. Right, so that's just integrating this equation from 0 to some distance r. Where the point y is that far away. So if I just rearranging this equation so that I have it in kind of the form I want, like up here, then I get firstly just looking at the left hand side, then I get h xt divided by 1 plus ch xt r is less than or equal to hyt. And then the same thing on the other side gives me hxt divided by 1 minus cht r. So, I mean, it's almost in the form that I wanted. So if r is equal to, let's see, 1 on chxt times 2, then here I have 1 minus a half, and here I have 1 plus a half. Okay, so if I have r is less than or equal to this, then I have this is less than or equal to 2hxt, and this is less than or equal to, so I get 3 on 2, 2 on 3, and then so I can put a half here, that's even less. Okay, so that's almost what I want. So I have this, but at the same time. Now, maybe if you wanted to prove that, if that was the only thing you wanted to prove, you could do that. If you didn't know anything about the time derivative, if you just had this fact, now you have this inequality here, that if you just have the gradient is bounded of h, the spatial gradient, then you know that in some small neighborhood such that the distance between x and y is less than or equal to, oh wait, I forgot to say inverse? Yeah, inverse. Less than or equal to this quantity here, then now I know that the h can't increase too much. Now when I want to also do the time derivative, that's basically exactly the same. I know that the time derivative, h minus 2 is less than or equal to c squared minus c squared. So now I'm integrating between s and t. So, and I know that s minus t is less than or equal to r squared. Then I get minus c squared t minus s. So s is in t minus r squared, comma t. So s is less than t. H y comma t to the minus 2 minus h y comma s to the minus 2, which is less than or equal to c squared t minus s. But I know that these are both less than or equal to r squared. CR squared, c squared r squared. And then just as before, if we just rearrange this, then I know that h y comma s to the minus 2 is less than or equal to h y s divided by square root of 1 minus c squared h y s r squared. Oh, sorry, t less than or equal to h y t square root of 1 minus c squared h y plus r squared. Okay, so now I already know how to bound yt in terms of h. Okay, xt. Okay, so in the end, I get sorry, that's not minus 2. Okay, so then using this condition here, r is less than or equal to this quantity, then I can get h y s to h x t half h x t. Okay, and I'll stop there. Does anyone have any questions?
Cool. Let's thank Vishnu for going through these estimates. Does anyone have any questions or comments about this proof for Vishnu?
Thanks, Vishnu. Look, tough question maybe, because
okay.
I don't expect you to have read maybe this far, but can you explain a little bit about why? So the inductive argument to get the higher derivative estimates. So I think I convinced myself pretty well how that works inductively without surgeries. So I'm just wondering why. So what you said that you need to bound the order there in the present.
Oh yeah, okay, yeah. Oh yeah, so
a little bit more about what you mean by that, I guess.
Yeah, well, so I don't really know, but
yeah,
it says there in the paper, it says
yeah,
this bound, this k0, that number is how many derivatives the singular set has. I'm not sure if that's helpful, right? So I kind of imagine it's like when you have a mean convex mean curvature flow, you can say something about the singular set, like okay, in dimension 2, let's say, it's not really relevant to this, but like in dimension 2, I guess you can say something about like kind of like this maybe the smoothness of the singular set. You know that it can't have any pinches, so maybe it's related to something like that. Because of the convexity estimate, you can't have any kind of pinches in the actual singular set. So I'm thinking maybe it's something related to that, where you just look in one direction and then maybe, I'm not sure really.
Okay, yeah, thanks. I thought so it's always confused me a little bit. Because I mean, on the one hand, you seem to be able to do it as higher order as you want, but maybe you just have to be more careful with accounting. Maybe I thought it had something to do with like controlling the actual necks that you're constructing or something like that. But yeah. Anyway, thanks.
Yeah, I think maybe we see what matters there when we have to actually do the surgery. Right? So you have to keep track of a certain number of derivatives and then do the surgery to control that number of derivatives and so on. Yeah, probably better to leave that till later, I think.
Yeah. Okay.
Well, thanks. Are there any further questions or comments for Vishnu? All right, then in that case, let's thank our speaker again. Awesome. Thanks, everyone. I'll stop recording now.